Okay, so the first one, A, my mean is NP, so that is 100 times 0.75, 75. And then my variance is going to be NPQ, so that's 75 times 0.25. So you guys got 18.75.
Yeah.
And then our variance, so our standard deviation would be the square root of that. Yeah, square root of 18.75, and you guys got 4 point what? 33. Terrific. And then next was the next one. Mean is 300 times 0.3, 90. Variance is 90 times 0.7, 63, and then sigma is 60, square root of 63, 7.94?
Yes.
Okay, good. All right. So 7.9, I think 7.9 is okay. All right. Next one, lab problem 10. So what is my n?
10.
What is my p, little p?
0.5.
0.5, great. So my mean is going to be 10 times 0.5, 5. And then my variance is going to be,
5 times 0.5.
yep, 0.25, 2.5, sorry. And then sigma will be the square root of 2.5, which is
1.58.
5.8. Okay, sounds good. I'll go with that. And this one totally makes sense, right? I mean, you can kind of think about it that way. If I flip a coin 10 times, how many heads do I expect? 5. Because half of them, right? I flip it 10 times, half of them should be heads. Multiply those, you get 5. So that's the great thing about the NP, it's just it's so obvious that can't even tell. All right, watching fireworks. So let's see, here, what's my n? What's my sample size?
1,000.
1,000. Sample of 1,000. Sample of, that's kind of your clue, right? That's your n. And then what's my p, little p?
21.
Yep, 21% of Americans, so that's little p. And so this one would be, mean is 1,000 times 0.21, 210. My variance is 210 times 0.79, right?
Yeah.
So that's,
165.9.
yeah, so I'm going to put Q is equal to 0.79. What'd you guys get?
165.9.
165.9.
165.
0.9. And then my standard deviation would be
12.88.
12.88. Okay, 12.9. Something like that. All right, great.
What answer would you want? 0.88 or
Yeah,
0.9?
I'm not really going to be that picky about that. There are things to worry about, and that's not something I'm going to. Some people like I'll be picky about other things. That's not my picky thing. I'm picky about the trees. If you guys haven't noticed, I'm really big on trees. Okay, so now we're done with chapter 5. We're going to start in on chapter 6. So pull out your chapter 6 notes. We're going to start in kind of easy with a very quick 2 or 3 minute review of chapter 3 stuff. So again, z values, z scores. Remind ourselves really quickly. What's our symbol for our population mean again? U. Population standard deviation.
Sigma.
Sigma. Great. Sample mean.
X bar.
X bar. Good. And sample standard deviation. S. Great. Don't forget, these guys are parameters. So mu is a parameter. Sigma is a parameter. They are the population mean or the population standard deviation. Any population whatevers, those are parameters. These guys are statistics. X bar and S. All right, quiz problem 5. A z-score represents.
Below the mean.
Yep. can you guys all say it together one more time? Ready? 1, 2, 3. The z-score. Oop.
That's so cool.
Okay, good. So that's more or less close enough. You get the idea. Perfect. Z values, right? And again, it could be a whole number right here, like this guy here. He is -3 standard deviations below the mean. He's 3 standard deviations below the mean. His z-score is -3. This guy is 1.5 standard deviations below the mean. His z-score is -1.5. This guy is 2.35 standard deviations above the mean, so his z-score is positive 2.35. But you can't use these guys unless they're whole numbers. You kind of have to find the actual z-score itself. And the way you do that is here. You figure out how far the value is from the mean. You take the value, you subtract the mean. That way, if it's above the mean, it's positive. If it's below the mean, it's negative. And then you take that difference and you divide by a standard deviation to get that in standard deviation, so you know how many standard deviations that is. For a sample, it would look like this. Z equals x minus x bar divided by s. So I'll ask you this. If we have a set of data items, normally distributed with a mean of 240 and a standard deviation of 32, find the z-score for 240. 15 seconds, go ahead. Talk to your neighbors about it? Check with your neighbors? All right, what'd you guys get? 0. 240 is 0 away from 240. Make sense? How far is 240 from 240? 0. It's right on it. So here's my mean, 240, and 240 is right on it. So it's going to have a z-score of 0. Make sense? Everybody on board with that part? Okay. Now, that's going to be on your homework at some point, so I wanted to point it out. It's an important thing for you to wrap your head around, to realize that at the mean, the z-score is 0. Okay, so let's get a reader for this one. Ivana, go ahead.
The shape and position of the standard distribution curve depends on two parameters, the mean and the standard deviation. Each normally distributed variable has its own normal distribution curve, which depends on the values of the variables mean and standard deviation.
Right. So this one, we care about the mean and standard deviation. Binomial, we care about the n and the p. This one's a little bit different. So this one depends only upon the mean and standard deviation. So, for example, look at the top one. Those two normal distribution curves have the same mean. They're centered at the same spot. But one is more spread out, has a bigger standard deviation, and one is more squished in, has a smaller standard deviation. They have different shapes. Their standard deviations are not the same. These lower two, they have the same exact shape. They have the same standard deviation. They're the same amount of spread outedness. They're equally spread out. However, their means are the same. It's shifted, right? The whole thing is shifted to this way because their means are centered at a different spot. Make sense? So, same standard deviation, same shape, different mean, different center. Here, same mean, same center, but different shape, right? One's like this and one's kind of more like that. So it means a different standard deviation. On your exam, I will absolutely ask you this. I'll point this thing out. Two samples that have the same distribution around their mean will have the same standard deviation. So let me get 4 people up here really quickly. So can I get you 4? You 4. Quickly, come up. Okay. All right, so huddle up, make a little huddle, like a football huddle. Yep, good. All right, great. Okay, so make sure you guys stay firm with each other, so you can't move. Okay, and shift 3 steps that way. Good. So their relationship to each other stayed the same. You guys can leave now. It's a good thing. So their shape stayed the same, but their center moved from here to there. You guys see that? So their mean changed. They all moved together. Their mean went from here to here. So their center was here. Now it's there. But their shape, how far each of them was around the mean, stayed the same. Their shape stayed the same. So their standard deviation was the same. Their positions were the same. But as a group they moved. So their mean changed. So if your center changes, then your mean changes, where you're centered around. But if your shape stays the same, then your standard deviation will stay the same. Here, let me show you what I mean. Here's a different way. I'll give you guys another. Well, first let me explain this part to you. So in other words, if you have a set of numbers, and say this has a mean of 7 and a standard deviation of 4.1. Mean of 7. If I add 2 to every single number, they all go up by 2. Their shape stays the same with each other. But because they're all increased by 2, then the mean goes up by 2. So you guys see what I'm saying? Because they all went up by 2. Right? So I'm thinking like this. These are the prices for a meal. Right? Food. If all the prices increase by $2, then on average you're going to be paying $2 more. Does that kind of make sense? But the standard deviation of them, how spread out they are, is going to be the same. So I will ask you, I'll say, here are some numbers. Add 2 to every number. What's the mean and standard deviation? So here's the numbers. They have a mean of 7 and a standard deviation of 4.1. If you add 2 to every number, what's the new mean and what's the new standard deviation? Talk to your neighbors, 15 seconds, go. Add 2, new mean and new standard deviation, what is it? All right, guys, what's the new mean?
9.
9. What's 7? It goes up by, you add up 2 to everything, goes to 9. What's the new standard deviation? 4.1. It stays the same. Good. Here's another visual if you want another visual. Here is a number line. I'm just going to put a bunch of numbers on there. Okay, I take these numbers and I move them this way. There's still the same amount of spread outness. You guys see what I'm saying? Their spread is the same. Their standard deviation will stay the same, but their mean has shifted. Does everyone see what I'm saying? So they will still have the same standard deviation because in terms of how spread they are from one another, that stays the same. The thing that changes is their mean, their average, because now they're centered in a different spot. Okay. Was that better than having everybody up here huddling and moving around? Who liked the huddle better? Who liked the line with the other lines better?
That was pretty cool.
Which was, the huddle or the lines with the lines? Okay, you like that better. Okay, I'll do that in the future. I won't torture more people. I'm just curious. All right. Here are some properties. Let's get Vanessa. Go ahead.
The total area under the normal distribution curve represents 100% of the population. As you can see, a higher percentage of the population is in the middle and fewer are on the edges or outskirts.
Right, so most of them are in the middle, fewer and fewer as you get through the outskirts. We have randomly assigned 100% to be inside of here because this represents the whole population. How much do we have in the whole population? We have 100% of the population in the whole population. So we've made this arbitrarily 100%. It's a probability distribution. So that means that If you add up the whole population, you should have 100% of it. So this area under the curve represents 100% of the population. Or 1, right? More properties. Ian, go ahead.
Normal distributions are symmetric, and you can also see the mean, median, and mode are all exactly the same and correctly shaped.
Right. So the mean, median, and mode are right here, smack dab in the middle, and it's symmetric. The left is the same as the right, which also means that half, since the median's right in the middle, half is below it, half is above it. Make sense? 50% is here, 50% is there. The total area of the curve represents 100% of the population. This is if you were to like break them out to like a couple decimal places each, then you'd get something really finely detailed like this. We said roughly what percent lies within one standard deviation? 68%. So if you add these two up, you get about 68%, you get 68.26%. So if you round to the nearest percent, it's 68%. This is a little more detailed. If you have that handout, you can use it for your homework if you want to. And then, if you look at this, about how much is in each half. So take a second with your neighbors and figure out about how much is in each of these halves here. So just take 30 seconds with your neighbors and find those halves. Go ahead. Feel free to get a calculator and just hit some numbers and divide things. That's totally fine, right? You don't have to do it in your head. That's kind of crazy.
I mean,
Use a calculator. It's okay to use a calculator. It's totally fine.
yeah.
Okay, what'd you guys get for the first one? 34%. Half of 68%. How about the next one?
47.5.
47.5%. Great. And the last one?
49.85.
49.85%. Good. Everybody okay with those parts? Because it's symmetric, right? Half here, half there. This is similar to a problem we did before. Do you guys remember this? We said this is 68%. So that means that if I take this part here and that part there, they better be the rest of it. If 68% is on the inside, then how much is on the outside? 32%. 68% is on the inside, 32% better be on the outside. So those two outsides had better total 32%. However, it's symmetric. So half should be on the left and half on the right, which means this should be 16% and this should be 16%. Make sense? Half and half. 32% divided by 2 equals 16%. Okay. Remember these are sort of the rough numbers, because remember 68% is an approximation, it's not exact. So I don't know whether, if anytime we say using the empirical rule, or anytime we say approximate, then we want you to use these numbers. If we don't say approximate or use the empirical rule, or use Chebyshev's, then we want fine detail with the tables or with the calculator, the normal CDF, which we're going to learn about in just a few minutes. But your clue to use these guys, these approximations, is when it says approximate. So on your homework, you'll get some things that say approximate. So, let's get someone to read this part. Let's see. Jaime, go ahead.
For example, say the height of all men in California are normally distributed with a mean of 70
inches,
Uh-huh.
and the standard deviation of 5 inches. And the normal curve will be similar to the one below.
Right, 70 in the middle, 65, 60, 55 out this way, right? So it would look kind of like that, right? Everybody, does it make sense to people? Okay. Each one of these is a standard deviation. Very, very often, we want to know the cumulative relative frequency. In other words, the percent of population that's less than a number or greater than a number. Like, what percent of men are shorter than 55 inches? Or what percent of men are taller than 70 inches? Something like that. That's something people want to know a lot of times. How many are less than this or greater than that? So, for example, what percent of men in California are less than 70 inches tall? What do you guys think? Take 10 seconds with your neighbor and figure out what percent of men in California are less than 70 inches. What is it, guys? 50%. It's half. You guys can see that already, yeah? What about less than 65%? Take a sec with your neighbors, try to figure that one out. Less than 65, sorry, less than 65 inches.
Oh.
What about that one there? It might help to think about this one. It's the inside. Find the inside first. If you find the inside, what's on the inside?
68.
Yeah, this is one standard deviation, so it's 68%. That might help you find the outside. So 60% on the inside, how much is on the outside?
32.
32. And remember, it's symmetric, so half on each side. What's half of 32?
16.
16%. About what percent are less than 60 inches tall? Here's 60 inches. Less than that. What percent is that one? So again, you might want to take a look at your thing here. Figure out what percent's on the inside here, guys? How many standard deviations is it?
2.
2?
So 95%.
95%? Okay, so what percent's on the, 95%'s on the inside, what percent's on the outside? 5%. How much in each side, in each half of that? Half of 5%, so 5% divided by 2, 2.5%. Okay, now here's a new question. Greater than 60 inches. So that means this part here, all the way out to infinity. What's that pink stuff there? There's 2 ways of finding it. Everyone find one of those 2 ways with your neighbors. 10 seconds. Come on. Okay, I will randomly call on someone in 5 seconds. Talk to your neighbors about it.
Because it's 80. It's that
Edgar. Oh, Edgar's not here. All right, fine. Alyssa Q. Greater than 60%. How'd you find it?
I'm sorry.
What's the probability that you're in the pink range? Talk to your neighbors quickly.
97.5.
Why? How'd you find it?
95 or 0.95 2.5.
Okay, so you could do that. You could say the other end must be over there. 97.5%. You're adding this 95% plus this part over there. Who found it a different way? There's another way of finding it. Who has the other way of finding it?
Just subtract the 2.5 minus, from 100.
Yeah, you can take 100%, the whole thing, because you know that this part, the red part plus the pink part, has to equal 1 or 100%. Right, Adam, is that what you're going to say?
Yeah.
So then you can take 100%, subtract off the 2.5%, and you'd get 97.5%. So there's two ways of finding that one. How about greater than 80%? This part over here, 2.5%. Why is it 2.5%? Because it's symmetric. If this part here, over here, is the same as that part there. It's symmetry. Everybody see that? So use that symmetry of these normal distributions to help you solve problems also. It's symmetric, which is super useful. Make your life easier. 7, see how it's symmetric? Do you guys see how these are the same? Right, from here to there, they're the same. Do you guys see that? It's just the other side of it. They're both 2 away. 1, 2 away. 1, 2 away. Right? Okay, so then here's the interesting thing. Mahika, go ahead and read.
What if someone is 64 inches or 63.26? We can find their z-score, but it won't be an integer. So how do we figure out what percent of people are greater or less than they are? We can make a table showing cumulative relative frequency for each height to the nearest hundredth of an inch, but that would be a lot of work and only collect this one set of data.
Right. So you could make a giant table that had every possibility for every single, for 60.5 inches, 63 inches, 64.7 inches. You can find all of those things and have this giant table. But it only applied to men in California or whatever this is. So the cool thing is, if we convert to z-scores and use z-scores only, then we have a table that's standard that can be used across any set of normal data. All you have to do is convert it to a z-score. And then these are the same for all of them if you just look at the z-scores. And the great thing about it is there's a table that has made up all of these things, and if you use your calculator, then all of them are stored in your handy-dandy calculator. This whole table is in there. They have it all calculatable and accessible there. So that's what we're going to look at next, is how to calculate those z-scores using your calculator. Or sorry, given a z-score, how to calculate those areas using your calculator. We're going to skip that one. I'm going to go in here. How about, who hasn't read yet? Ulysses, go ahead and read.
How to use the calculator to find the area under the curve, percent of the population. For normal CDF gives you the area between two z-scores. You could find the function normal CDF, which gives you normal CDF.
Yep.
And
So
then
it looks like this. When you type in normal CDF, it gives you this with a little parentheses. Keep going.
And then you type in the z-scores separated by a comma. Left z-score, right z-score.
So for example, to get the z-score, the area between -1 and 1, I'd get normal CDF on my calculator, and then I'd put in -1, and then the comma, which is about the 7, and then +1. And that would give me 0.6827. So normal CDF will give the area between any two z-scores that you feed it. You feed it a left z-score, which is the lower one, and the right z-score, which is the higher one. If you do it the opposite direction, it's going to give you a negative area. So you would probably prefer not to do that. So, right, so if I want to find the area to the right of -1.14, a z-score of -1.14, I do normal CDF of -0.14. And what's the z-score way, way, way over there? What's the z-score way out that way? What's the number way out that way? In a number line. What's the number way over there in a number line?
99.
Infinity. Right, infinity is way over there. But any large number will do, especially when you're talking about standard deviations. You can use your grandmother's age. Right? How old's your grandmother? Someone give me their grandmother's age. 60? Great. 60 works great. You can use 60. Perfect. That's good enough. Because in terms of standard deviation, 60 is a lot. You can even use your age, honestly, because in terms of standard deviations, your age is a lot. Assuming you're all over 10. Okay. What does this mean? This means that 67.29% of the population is more than that many standard deviations away from the mean. More than that way. Here's another thing. Say, it also can be written like this. The probability that z is between these two numbers. That's a probability that a member of the population has a z-score between 0 and 2.53. If you do normal CDF of 0, 2.53, you'll get 0.4943. That means that 49.43% of the population lies between z-scores of 0 and 2.53. So it means that if I randomly pick somebody, there is a 49.43% chance that person has a z-score between those two values. Right? So that's another way of looking at it. A randomly selected member of the population has that percent chance of having a z-score between those two numbers. These are all connected. Shh, you guys, quiet. Mahika, thanks for volunteering. Go and read.
Using your TI calculator and normal CDF to find areas from z-scores, press second
Bars.
and then choose distribute DISTR and down to 2, normal CDF, left z-score, right z-score. Use negative 999 to go all the way to the left and 999 to go all the way to the right. Example is normal CDF, negative 999 to 1.2 would be the area to the left is z-score of 1.
Right? Because that number way over there would be negative 999. But you could just use negative your age. That works. That's plenty large enough as well. You guys didn't think you were old, did you? Ha, ha, ha. All right, so here's the example. And again, this is what I would do first. I would like you to draw a picture. Draw a picture, put in a little mark where the middle is. So draw this curve first and then the line, because the line's easy to draw. A little mark where it is. And then 1.2, negative 999, that's way over here. All right, that's way out this way. And 1.2 might be, I don't care where you put 1.2. It should be, is it positive or negative? 1.2? Positive, so it should be on the right or the left? It should be on the right. Everybody follow that part? So somewhere over here, put in 1.2. Draw a line straight up. Do I want less than that or greater than that? Negative 999, that's my left one. So that means I want this side. Everybody okay with that part? So that means my z-score is going to be negative 999. So I'm going to do normal CDF of negative 999, comma 1.2, and that's what you would do on your exam to show your work. And then you do this. Turn on your calculator, and you would do second, this little blue bar, bars, see the little bars right there? Bars, and then go down to normal CDF. Not PDF, CDF. Normal cumulative distribution function, CDF. Hit enter. I want the left number for a negative number. You cannot hit the minus sign. You have to use this little negative next to the enter sign down here. You guys see that one? Everyone see it? Everyone look up. You guys see this? Right there, down here. Negative. What's your age? Your grandmother's age? 60? Great. Comma 1.2. Enter. 0.8849. 0.8849. Good? That's the area from negative 999 up to a z-score of 1.2. Let's do another one together. Find the probability using a standard normal distribution. Is this on your notes? Yes? No? Oh, I think it's later on. Sorry. I'll do this one. That's fine. We can do this one. So put a little dot in the middle. Negative 1.43. Where is that? Left side or right side?
Left side.
Left side. Negative 1.43. Line straight up. says 0. Where's 0?
0.
Right here, line straight up, shade in between them. And then you're going to do normal CDF of negative 1.43, comma 0. So let's do that one together. Again, second bars right here, go down to normal CDF, the second one. Enter, negative, got to use this button down here, negative 1.43, comma 0. Enter. If you get an error, that's because you used the minus sign instead of the negative sign down here. If you got an error, that's because you probably used the minus sign, right? Negative, so that's 0.4236. We usually do 4 decimal places on these. Okay, so that's one last thing I want to talk about very quickly. What was that?
Yeah, because mine goes somewhere else too.
What was that?
Can you show us on the calculator? Because it's not.
It goes somewhere else.
Oh, so if you have a fancy calculator,
No.
Yeah, the 84.
then yours will do, here, give me yours.
It's like up and down.
Give me a fancy one. Perfect. If you have a fancy one, I'll show you guys really quickly. If you have a fancy one, then you get this instead. The lower one is negative 1.43, negative, zoom out a little bit,